Okay, good morning, everyone. Okay, so we consider the hyperbolic functions. Since this topic seems to be new to many students, let me go over some definitions and some key properties of the hyperbolic functions. So, the hyperbolic functions are derived from the exponential functions e to the x and e to the negative x. And as I said, the hyperbolic sign is defined by this, and hyperbolic cosine is defined by this one. So that hyperbolic sine is an odd function passing through the origin, and the hyperbolic cosine is an even function. And since these hyperbolic sine or hyperbolic cosine are defined with respect to the exponential functions, we could easily identify their domains and the range. Especially the range for the hyperbolic sine is from negative infinity to plus infinity. And the range for the hyperbolic cosine is all the real numbers starting from 1 to infinity. Right? And then the derivative of a hyperbolic sine was hyperbolic cosine, and the derivative of a hyperbolic cosine was hyperbolic sine. Given these two definitions of hyperbolic sine and hyperbolic cosine, we could define the hyperbolic tangent or the other three hyperbolic functions. Okay, so these are the definitions of hyperbolic functions. So these are the definitions of hyperbolic functions. And then we could derive some identities by the definition, using the definitions of hyperbolic sine and hyperbolic cosines. So we could easily derive this, and I showed some examples the other day to confirm these identities. And not only the identities, but we also have some the formula for the differentiation. So these are the differentiation formula for the hyperbolic functions. Then we extended this formula to their inverse functions. And as we know, the inverse function can be defined only when the given function is one-to-one. And in case of hyperbolic sine, it is one-to-one on its whole domain, while hyperbolic cosine is not one-to-one on its whole domain. So we just had to take just one half of the domain so that the hyperbolic cosine on this restricted interval becomes one-to-one function. So in other words, we can consider the inverse of hyperbolic sine or hyperbolic tangent without any string. But in case of hyperbolic cosine, we need to restrict the domain to non-negative values so that the function becomes one-to-one. And in that case, we can think of the inverse function. Now, given this inverse function, we could derive the derivatives. Oh, before we do that, the inverse of hyperbolic sine or cosine can be expressed in terms of the logarithmic functions. And if you use this definition, the expression for in logarithmic functions, it might be easier to derive many formula, especially the derivatives of the inverse functions of these hyperbolic functions. So if we use them, we could derive these inverse functions. Okay? So as an example, as an example, if I have, oh, this is okay. So we already considered this one. So as an example, so let me consider some example. So using this, if I have, say, the inverse of hyperbolic sine of not x but say say hyperbolic cosine of x, something like this. So if I have this y function, and how can I find the dy dx? So if I ask you to find dy dx, the first method is the first way is using the chain rule with this formula. So we have the composite of two functions. So we can use the chain rule. We first differentiate the outer function. So if I differentiate the inverse of hyperbolic sine, we get this one. 1 over square root of 1 plus x squared. So the chain rule says we need to first evaluate this derivative at the inner function. So that means 1 over square root of 1 plus hyperbolic cosine square. And then I need to multiply the derivative of the inner function, which is hyperbolic secant. So the answer will be I'm sorry, not hyperbolic secant, hyperbolic sine. So hyperbolic sine of x over square root of 1 plus hyperbolic cosine of x squared. So that is what this is one way to derive dy dx. Another method is using the take the hyperbolic sine function on both sides of the equation. Then the left hand side becomes hyperbolic sine of y equals to the hyperbolic cosine of x. And then if I differentiate both sides with respect to x, then when I differentiate the left hand side, you get hyperbolic cosine of y times dy dx equals to the derivative of the hyperbolic cosine, which is hyperbolic sine. Oops. So dy dx will be hyperbolic sine of x over hyperbolic cosine of y. But the problem is we do not know this hyperbolic cosine of y. Actually, I gave you the expression, okay, some function in x variable is given. So what I am expecting is a certain expression in x, but I do not know hyperbolic cosine of y, right? So I need to express this hyperbolic cosine of y in terms of some expression in x. Now, please remember that we know that the expression of hyperbolic sine of y, that is hyperbolic cosine of x. So since we have this, and we have the formula that hyperbolic cosine of y squared minus hyperbolic sine of y squared is 1. So hyperbolic cosine of y will be squared will be 1 plus hyperbolic sine of y squared. And since hyperbolic sine of y is hyperbolic cosine of x, we have this expression. And so hyperbolic cosine of y will be plus or minus square root of 1 plus hyperbolic cosine of x squared. Now please remember that hyperbolic cosine of y is always non-negative. Actually, hyperbolic cosine of y for any y value is greater than or equal to 1. Okay, so since hyperbolic cosine of y is always greater than or equal to 1, the hyperbolic cosine of y must take the positive sign between these two. So if I plug in that expression into this, then we get hyperbolic sine of x over the square root of 1 plus hyperbolic cosine of x squared. So if you know this result, we can directly apply the chain rule combined with the formula to get this result. If you forgot that formula, what you can do is you can apply the hyperbolic sine function on both sides of the equation, and then you can use the implicit differentiation. So there may be some other ways, but these are two simple ways to get dy dx. Okay. So so that's what we considered in the section 11 of chapter 3, and let's go to the next chapter. So here we want to derive some theorems, okay, from the general differentiation formula. Okay, and this section considers the maximum or minimum. Okay, and this section is quite important if your research field is related with some kind of optimization. In other words, if you want to minimize certain utility function or objective function, or sometimes you want to maximize a certain function under the certain constraint, right? So if your research field has that kind of question, that kind of problems, then this section might be quite useful and interesting. Okay, so in figure 1, suppose that we have the graph in pink as in figure 1, and suppose that we want to find the maximum, the largest value and the smallest value that this curve can take. Then as you can see, this value at 3 seems to be the largest value of the function, and the value at 6 seems to be the smallest value. So if I have the graph like this, then sometimes we can find the largest value or the smallest value from the figure. The problem will be a little bit complicated if your graph is a little bit funny like this. In that case, or if we go down like this, then actually, but that's the real world situation. And in that case, finding the smallest value seems to be a little bit challenging. You may find some approximate value of the largest or the smallest value, but the finding the exact value seems to be a little bit difficult. right? So in that case, we need to apply some mathematics. But before we consider the mathematics, let me introduce some terminologies. I mean, I want to define some terms, okay, and then we want to derive some theorems. Okay, so first, so if the value of the function at some point is greater than or equal to the function value at all points in the domain. That means this f of c is the largest value. In English, we say f of c is the largest. It is the largest value. But in mathematics, if that's the case, then we say that the f of c is the absolute maximum. Okay, so f of c will be the absolute maximum, or sometimes global maximum, if the value of the function at that point is greater than or equal to any other value. And if f of c is the smallest value in English, in other words, f of c is less than or equal to the function value for all x in the domain, then we say f of c is an absolute minimum, or sometimes global minimum. Sometimes if the context is clear, then you may omit this absolute or maximum, and we just say f of c is an maximum if that f of c is the largest value. And if f of c is the smallest value, then we say f of c is the absolute minimum or global minimum or just simply minimum. And the maximum and the minimum values of f, if they exist, okay, then the maximum and minimum values of f are called the extreme values. So when I say f of c is an extreme value, then that means f of c will be maybe the largest value or the smallest value, or mathematically speaking, it is an absolute maximum or absolute minimum. Okay, so extreme value includes both maximum and minimum values of the function. So in this figure 2, the function has the largest value at d. So the function value at d is called the maximum value or absolute maximum or global maximum. So global or absolute maximum. And the smallest value, it seems to be f of a seems to be the smallest value. So f of a is the minimum, or you may say absolute minimum, or global minimum, or just simply minimum. Okay, so if this is and if the interval from a to this point is the domain, then okay, so if this is the domain of the function, okay, so if then f of d is the global maximum and f of a is the global minimum or absolute maximum or absolute minimum. Okay, now In case of point C, f of c is not the minimum value. I mean, f of c is not absolute minimum. But if I zoom in, okay, in this figure, this point is the smallest value, all right? When I just look at, if I just look at the portion of the graph given in this slide, right? So on this screen, this value is the smallest value. Mathematically, if that's the case, then we say this point is a kind of minimum when I zoom in, right? So in that case, in other words, if 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 you can find some interval on which the value at c is the minimum, the smallest value, in that case, we say f of c is a local minimum. Okay, so f of c is called a local minimum, meaning when I zoom in, the value at c, value of the function at c may be the smallest value on certain interval. So if that happens, then f of c is called a local minimum. One more time. So if you can find some interval around the c, say from alpha to beta. So if you can find certain interval within the domain, and f of c is the smallest value on that interval. Okay? In that case, we say f of c is a local minimum. The value at e is also a local minimum because I can find some small interval around e on which the value at e will be the smallest value, right? I mean, I can zoom in, then on that interval, this value, the value of the function at e will be the smallest value. So if you can find such interval, okay, and on that interval, the value of the function at certain point is the smallest value, then we call such point as a local minimum. In case of B, we have the opposite situation. At B, f at B is not, okay, so when I look at this f of B, when I just look at some portion around B, you can find some interval, and on that interval, probably the value of the function at B will be the largest value. So the value of the function at B in that sense is called a local maximum. Well, then how about D? Around the D, I can also find some interval, as you can see, and on that interval, f of D will be the largest value. So f of D is a global maximum, but it is also a local maximum. Now, then how about point A? Well, if I consider any interval around A, if I consider any interval, then actually one half of the interval to the left of A, this portion is outside of the domain. Please remember that this is the domain we considered in the beginning. So if that interval is the actual domain of the function, then whenever I consider any interval around A, some portion of the interval will go outside of the domain. In other words, we cannot find any interval around A such that f of A is the smallest value. So f of A is the smallest value on the whole domain. So that's why it is called the absolute or global minimum. But f of A is not absolute minimum. I'm sorry, not local minimum, because I cannot find an interval. I cannot find any interval around A such that the value for f of A is the smallest value on that interval. Okay. So So in figure 2, many students got confused. Some people think that if certain value f of d is a global maximum, it will be always global, the local maximum. And f of a is the global minimum, it will be a local minimum as well. That's what some people think, but which is not true, which may not be true. Okay. So we say f of c is a local maximum if it is the largest value, it is largest value around c when x is near c. In mathematics, when I say some point is near c, then that means it is true on some open interval containing c. So that means we should be able to find some interval around C, around, okay? So that you should have some portion to the left and to the right of the point C. In that case, we say f of C is a local maximum. And if the value at C is less than or equal to any other point on certain interval, we say f of c is a local minimum. So please be careful. Okay. So global maximum may not be a local maximum. In a similar way, if you have the global minimum, that point, that value may not be a local minimum. And we saw one example in figure 2. So let us consider the figure 3. So at point 4, the function value at 4 is definitely a local minimum because I can consider the interval I. And on that interval I, the function has the smallest value at 4. And the value at 8 is a local maximum as well. And the function value at 12 is another local minimum. If this is the graph of certain function on its whole domain, then the value at 12 is also on global minimum. And what is the global maximum? The value here is the largest value. So this is the global or absolute maximum, but it is not a local maximum. Because I cannot find the interval around this point on which the value at the point it becomes the largest. So the global maximum may not be a local maximum, okay? In particular, the so if you have a global maximum or global minimum at one of the endpoints of the domain, then the global maximum may not be a local maximum. Let me erase this. Now, let us consider the example 2, where in figure 5 we have the curve of the cosine x. As we know, the largest value that this cosine x can take is 1, and the smallest value is negative 1. So this 1, these values are the absolute maximum, and it is also the global maximum. And this negative 1, these are local and minimum, absolute minimum. This is a local minimum, as you can see, because I can find any interval, right, around the point on which this point is the negative 1 is the smallest value, and it is an absolute minimum because we cannot find any value smaller than negative 1 for the cosine x. So figure 2 shows that the absolute maximum or absolute global these absolute values, these extreme values or local maximum or local minimum, these values may not be unique. So the figure 5 shows that local or global or absolute maximum or minimum, so you may have multiple absolute values, or I mean multiple absolute maximum or multiple absolute minimums. We will consider a few theorems regarding these extreme values. So if f is continuous on some closed interval. When I say the closed interval, that means the interval includes both endpoints. So if you have such closed, so if your function is continuous on a closed interval from a to b, then so if your f is known to be continuous, then you always have an absolute maximum and some absolute minimum. Okay, so if your function is continuous on the closed interval, then in any situation you always have an absolute maximum and absolute minimum. So we have two conditions. Your function is continuous and the interval I'm considering includes both endpoints, so that the interval I'm considering is a closed interval. So under these two requirements, your function always have an absolute maximum and absolute minimum. These are some examples. So in figure 8, I'm looking at three different continuous functions. So in each graph, I always have an absolute maximum and absolute minimum. Absolute maximum, absolute minimum. Multiple absolute maximum and absolute minimum. Of course, this point is absolute and local maximum, and this is absolute minimum, and it is also a local minimum. Here is absolute and local maximum, and this is a absolute minimum but not local minimum. These two are absolute or local maximum, and the value at D is absolute or local minimum. So please be careful with this point, because at that point this is not local minimum. And as I said, the previous theorem requires two conditions. Your function must be continuous, and that continuity is given on some closed interval. In that case, your function will always have on the largest value and the smallest value. In other words, absolute maximum and absolute minimum will always exist. But if those two conditions are not satisfied, for example, if your function is not continuous, even though your function is defined on the closed interval from 0 to 2, even though the second condition is satisfied, your function may not have the maximum or minimum value. In this figure 9, absolute minimum exists, but there is no absolute maximum, because as you can see at this point, the value at 1 is this one. We don't know the actual value though. Okay. And so the function has no global maximum. Now, one on the right, figure 10 shows that even though your function is continuous, but if that continuity is given on some open interval, not closed interval, then absolute minimum or absolute maximum may not exist. So in this figure 10, there is no absolute minimum and there is no absolute maximum. So those two conditions, continuity and closed interval, are required. Okay. I already considered this. Yeah. Now, let us consider the following figure 11. Okay. So the extreme value theorem says that a continuous function on a closed interval has a maximum and a minimum value, but it does not tell us how to find these extreme values. Now, let us look at the figure 11. So at C, we have a local maximum, and at D, we have a local minimum. Now, at point C, where you have local maximum, the tangent line is horizontal. And similarly, at D, where you get the local minimum, tangent line is horizontal as well. Okay, so we have one theorem called the Fermat's theorem, which says if your function has a local maximum or local minimum at certain point, and if you can find the tangent line at the given point, in other words, f of f prime at C exists, that means you can find the tangent line at the given point. Okay, so if you have a local maximum or minimum at certain point, and if you can find the tangent line, f prime of C will be 0. So f prime of C exists, that means, so f prime of C exists. That statement in English implies that the tangent line exists at point C. Okay. Then the conclusion is f prime at C is 0. That means f prime of C is the slope of the tangent line. Right? So this is the slope of the tangent, and if the value is 0, then that means the slope is 0, so that the tangent line at C is horizontal. In other words, the line will be parallel to the x-axis. Okay, so the tangent line will be parallel to the x-axis. That's the Fermat's theorem. Then, okay, we have this nice theorem. Then one question you may ask will be, Okay, then how about the opposite? If if tangent line is okay, so okay, before we consider that converse, let us think about some examples. So if f of x is x cubed, f of prime of x is a 3x squared. So f of prime, if I plug in 0, then when x is 0, f of prime at 0 is 0. So what does that mean? F of prime at 0 is 0. So, so the tangent line is horizontal. Then do I have a local minimum or local maximum at 0? If you look at the graph, there is no maximum or minimum at 0. Okay, so what does that mean? Okay, so we just observed one theorem called the Fermat's theorem, which says, if your function has a local minimum or local maximum, and if you can find the tangent line must be horizontal. That was the claim made in this Fermat's theorem. Now, this example shows that converse may not be true, right? As in case of x cubed function, even though the tangent line exists and it is horizontal, so the tangent line at 0, first of all, it exists and is parallel to the x-axis, right? But what is the problem? There is no maximum or minimum. So that means the converse may not be true. Then how about this example? Let us consider the absolute value function. Okay. Now, definitely this function has the smallest value at 0. So f of this 0 will be the absolute minimum or local minimum. So this is definitely a minimum value. Okay. It is a minimum value, but what's the problem? F prime at 0 does not exist. In other words, the tangent line at 0 does not exist. So Fermat's theorem required two conditions. First of all, if the function has local minimum or local maximum. Secondly, the tangent line exists at the given point. Then the conclusion is that the tangent line must be horizontal. And we observed two examples. In example 5, even though the f prime at certain point is 0, there is no maximum or minimum at the point, right? In example 6, even though you have a local maximum, even though you have the global minimum or local minimum at 0, the function does not have the tangent line at the point. So when you read some mathematical theorem, please, you need to be careful. You need to check all the conditions. Now, one more definition. We say C is a critical number of a function if so there is either or statement. So either f prime of c equals 0. So that means the tangent line exists and it is horizontal. So f prime of c equals 0. That means the tangent first of all, tangent line first of all exists and the n is horizontal. Or, so we have either or. So either the tangent line exists and is horizontal, or f prime of c does not exist. So that means the tangent line does not exist. So either the tangent line exists and is horizontal, or tangent line does not exist. In that case, at some point, then we call that point C as a critical number. So, oh, one minor comment. When I say a critical number, that is a number in the domain such that tangent line is horizontal or tangent line does not exist. When I say extreme values, it represents the global maximum or global minimum value. So when I say the extreme value, that's a y value. And when I say a critical number, then it is certain value for x variable. So what was the claim? What was the statement of the Fermat theorem? Fermat theorem says if your function has a local minimum or local maximum at a certain point, then then local maximum or minimum at some point, and f prime of c exists, then f prime of c must be 0. So in other words, if your function has a local maximum or minimum at some point, then either your f prime of c does not exist, or it exists but the value is 0. So that is the Fermat theorem. In other words, if f is a local maximum or minimum at some c, then this c must be a critical number. So if your function has a local maximum or minimum at some point, then this c must be a critical number. Either f prime of c does not exist, or if it exists, the value must be 0. F prime of c must be 0. So that is the definition of the critical number. So if I want to find, okay, I have one message. The, okay, I have one message from one of the students asking, okay, will the midterm exam be more practical question or will it be more conceptual? Um, it will be, okay, it will be closer to the practical question. Yes. So probably I will ask you to calculate some problems in most cases. There may be some question related with the proof. I don't have the problem set, so I cannot guarantee, okay? But yeah, everything is possible. But usually I do not ask you to prove some theorem, okay? As in the slide. If I give you a problem asking certain proof, probably I will give you certain practical question with some numbers, and then I will ask you to check certain property or something. Yeah. So probably I will show some sample problem before the exam. Once I cover all the sections, probably uh, at the current speed, probably I will complete the chapter up to chapter 5 uh, probably a week before the midterm, or at least one day before the midterm. So I think I have some time to show you some sample toy problems before the exam. Okay. Hope that answers the question. If that still is not clear, then let me know. Anyway, we have one technique, okay, to find the absolute maximum or absolute minimum of certain function. Okay, but there are some conditions. Your function must be continuous, and that function must be defined on some closed interval. And if you want to find the absolute maximum or absolute minimum, then please find the values of f at all the critical numbers of f. So what did I tell you? What is the critical number? I told you a moment ago, just a minute or two ago. What is the critical number? There are two possibilities for a critical number. If some c is a critical number, okay, there f of c, so either f prime at c does not exist, or f prime c is 0. Some students neglect this portion, okay? So please be careful. If we want to find the absolute maximum or absolute minimum, then you first find the values of the function at the critical numbers. So that includes the points where your function is not differentiable. Okay? You evaluate the function on that point. If you have several critical numbers, you need to evaluate your function at all those points. And please also find the values of f at the endpoints. Even though these endpoints are not critical numbers, please find the values at this left endpoint and the right endpoint. So you have these values. Among these, the largest one is the absolute maximum, and the smallest value is the absolute minimum. Okay? So please remember this. So for example, if I have certain function whose graph is like this, and suppose that that's the end of the graph of the function, so that this function is defined on this closed interval, then if this is A, B, C, D, E, then first of all, critical numbers. Critical numbers are points where your function is not differentiable or function has horizontal tangent line. So C, D, E are critical numbers. You also find the values of the function at these two endpoints. So among these five values, the largest one is the absolute maximum and the smallest one is the absolute minimum. Okay, so you must include these C and D where your function is not differentiable, because that is still a critical number. Okay, so that's the section 1 of chapter 4. And then we want to consider some two important theorems called Rolle's theorem and mean value theorem. So the Rolle's theorem is simple. If if your function is continuous on the closed interval from A to B, okay, and it is differentiable on this interval without the endpoints, because so far we didn't study how to differentiate certain function at the end of the interval, right? We didn't study that kind of a property yet. So we just restrict the domain for the differentiability. So in number one, your function is continuous on the whole interval from A to B, including the 8A and B. So when I say the closed, meaning that means including these endpoints A and B. And your function is differentiable on on the open interval from A to B. And f of A and f of B are the same. So at these two endpoints, the function values are equal, the same. In that case, there will be some number C in A and B. So that means this C is some point inside the interval. Okay, and we call such a point in math as an interior point. Such that f prime at C equals to 0. So what does that mean? Tangent line is horizontal. Okay, so that means so f has so that means f has a horizontal tangent line at some point between A and B. So at some interior point, so I said that point as an interior point. So we have some point in the middle of the interval where the tangent line becomes horizontal. That is the claim of the Rode theorem. And if we look at the graph of several functions, this claim is simple. So if you look at these four examples, four different types of functions, so all four functions are continuous from A to B, including the endpoints, and differentiable at every point on that interval except two endpoints. Then, as you can see, you have horizontal tangent line at some point in the middle. So here at C in B, your tangent line is horizontal. Well, in case of A, any point other than A and B will be a C point, so that your tangent line is horizontal. In C, so in A and C, this C may not be unique. So this C may not be unique when we look at the graphs in A or C. In case of a B and D, such a C is unique, right? But anyway, the situation is this: if you have any function like this or this, any function, or if you have, say, any function, as long as it is continuous and differentiable on certain interval. And of course, when I say the continuity, I'm including the endpoints. And when I say differentiability, I'm just considering all the points except these two endpoints. So if you have such nice smooth function, and if f of A and f of B are equal, then there must be certain point where tangent line is horizontal. And as I said, such a point may not be unique. So this is the Rode theorem, and this Rode theorem is quite clear when you look at the graph. Now in example 2, let us consider the following problem, which is quite interesting. This equation, we have a cubic equation, and that has prove, okay, what is the problem? Prove that this equation has exactly one real solution. Okay, exactly one real solution. Then what should I show? I first need to show that the problem has a solution, the existence of a solution. And then I need to show that the solution is unique. So you have exactly one solution, the uniqueness. So for this problem, you need to show two things. Okay. Then we can use the intermediate value theorem to show that a solution exists. And then we will use the Rode theorem to prove that the solution will be unique. Oh, but what is the intermediate value theorem? If you have, what is the intermediate value theorem? What, what does it? If you have certain function from A to B, and if your function is continuous, then when you choose any value So if this is your f of b, and here is my f of a, then when you choose any value between f of a and f of b, there will be some point c between a and b such that this L is the value of the function at c, and such c always exists between a and b. That was the intermediate value theorem, right? So let us consider this problem. So to answer this, let me define f of x by this cubic polynomial. And if I evaluate this function at 0, so I mean if I plug in 0 for x, the value you get -1, which is negative. And if I evaluate this function at 1, the value is 1, which is positive. So the intermediate value theorem says, if I choose any value between -1 and 1, there will be a c such that f of c equals that L value. So let us consider the case when L is 0. There will be some c such that f of c equals to 0, right? So there will be a number c between 0 and 1 such that f of c equals to 0. Then what does that mean? That means at point c, c cubed plus c minus 1 equals to 0. That c is one of the solutions. So the intermediate value theorem guarantees the existence of a solution. Then how can I prove that there is only one solution? So for that purpose, I want to use the Rolde theorem. So to show the uniqueness, let me assume that we have two solutions. Okay, so suppose that it has two solutions, say A and B. Okay, so suppose that we have two solutions. So f of A is 0 and f of B is also 0. Then this function x cubed plus x minus 1 function is a polynomial. So it is differentiable on this interval from between a and b, and it will be continuous on the closed interval from a to b. So the Rolde theorem can be applied. What does the Rolde theorem say? There will be a number c between a and b such that f prime c equals 0. Okay? That means, so there must be such a point, right? Now what is f of x? X cubed plus x minus 1, and this function must have a point to c. If there are two solutions, then there must be c such that f prime of c equals 0. The problem is f prime of x is 3x squared plus 1. It is always greater than 1 for any x, because x squared is non-negative. So we cannot find any c where f prime becomes 0. So we get a contradiction. Why do I have a contradiction? Because I assumed that there are two different solutions, right? So that first assumption caused this contradiction, and we get this situation here. So since we have this contradiction, our assumption is wrong and there will be only one solution. Okay, so by using the Roger theorem, we could prove the uniqueness. Anyway, thank you for listening and have a nice weekend, even though it is Wednesday. Okay, so please have a nice weekend, and if you have any questions, please let me know. Okay, see you next week.